So the test 3 has been graded. The grades are posted. So the grades were not great. So we don't want to be too distressed by the grade if it's low, because remember we have a test replacement policy. Your final exam will replace the lowest of your 3 in-class test grades, and the final exam will be kind of more routine than this test was. On the other hand, kind of not terribly surprised that the grades on test 3 were low given the circumstances, and also given the fact that only one student has scheduled any WebEx office hours. Only a very small number of students have asked questions about the recommended problems, and most of the video lectures have fewer than 20 views. So I know that most of you are not watching the lectures. So if you don't watch the lectures, then we can't reasonably be expected to do very well. So I'm going to go through the test and work the problems. So the first problem was this identity about the Fibonacci numbers. This one was directly out of the book, and it was, I think, right between two problems that you were assigned in the recommended problems. So this is one of the even numbered problems, and you were assigned the odd numbered problems around it. So we're going to prove this one by induction. So I'm going to prove it by induction. This is my P of n proposition. So first I'm going to prove P1. So P1 is F2 times F0 minus F1 squared. And it was stated in the problem that we're using F0 is 0, F1 is 1, and then after that we just add. So this is 1 times 0 minus 1, which is negative 1, which is negative 1 to the 1, which is what it's supposed to be. And so we've confirmed the base case. Now we want to do the inductive step. So here's the base case. Now we want to do the inductive step. So so assume, so we make it very clear what we're assuming. I'm going to assume Fn minus 2 minus Fn minus 1 squared equals negative 1 to the n minus 1. I'm assuming Pn minus 1, and I'm going to use this to prove Pn. You can assume Pn and use it to prove Pn plus 1. It's the same thing. Okay. So I'm going to say, so I'm going to assume this, and then use it to prove the next case. Okay, so the next case would be Fn plus 1, Fn minus 1 minus Fn squared. And I would like for this to come out to be negative 1 to the n. That's my goal, is to prove that Pn is true, given that Pn minus 1 is true. Okay, so this is the left side of Pn, and I need to somehow make it come out to be the right side using Pn minus 1. Okay, so here I'm going to use the definition of the Fibonacci numbers. Fn plus 1 is Fn plus Fn minus 1. And this Fn minus 1, I'm going to leave it alone. The reason I know to change the Fn plus 1, but not change Fn minus 1, is because I look at Pn minus 1 and see what's there. There's no Fn plus 1 here, so if I want to use Pn minus 1, I probably don't want Fn plus 1 there. Okay. And I also look here, I don't see any Fn minus 3, and if I change Fn minus 2 to Fn minus 1 to Fn minus 2 plus Fn minus 3, I'm going to have an Fn minus 3 there, not here. So if I'm going to use Pn minus 1, I want to change things here so that I only have what's here. And now I'm going to have minus, so this is an Fn squared. I'm going to leave one of the Fn's there. The other one I'm going to replace it with Fn minus 1 plus Fn minus 2, right? And I can do that because that's how the Fibonacci numbers work. Fn minus 1, or Fn is Fn minus 1, Fn minus 2. Okay. So here, because I've gone past the base case, I know Fn is not 0, or n is not 0 or 1. It's at least 2. So I'm in the recursive part of the Fibonacci numbers. Right. So now I'm going to distribute. I get Fn minus 1 plus Fn minus 1 squared minus, let me distribute over here, Fn minus 1 minus Fn minus 2. I'm going to rearrange this, so this part and this part cancel. I'm going to have minus Fn minus 2 minus Fn minus 1 squared. And now by Pn minus 1, this part in parentheses is negative 1 to the n minus 1, and then negative 1 times that is negative 1 to the n. Right, so we did it. So here we have some counting problems. So these counting problems were all intended to be just free points. So I expected everyone to get all of these counting problems because they were very straightforward. So I have a string of length 100 and I'm going to use zeros and ones. So I have 100 positions in the string. Each one can have either 0 or 1. So for every position there are 2 options, so I have 2 to the power 100. Okay. 2 options for the first position, 2 options for the second, 2 for the third, 2 for the fourth, etc. So this is the total number there. Same thing here. I have 3 choices for each position, so I get 3 to the power 100. 3 choices for the first spot, 3 choices for the second spot, 3 choices for the third, all the way down 3 choices for the 100th spot in the string. Okay. So some of you said the strings can't start with a 0. And they can. So strings are not the same thing as a number. So if I have a number, I'm not going to write a leading 0. But strings are not the same. I mean, a string is symbolic. These things are treated as characters and not numerical values. So strings can start with a 0. So how many sequences of length 100 do I have using the numbers 1 through 100? So this is what we called. Okay. So these are sequences. So order matters. So I don't have repetition, so I'm using this. It's just 100 factorial. It's just the number of ways to reorder the 100 elements. I'm going to write, if I'm going to make a sequence of length 100 using 100 numbers, then all 100 numbers are going to be in the list. It's just the only thing that matters is the order. There are 100 factorial ways to reorder them. So I have 100 choices for what I'm going to put in the first place in the sequence, and then 99 choices for what goes second, and then 98 for the third, etc. All the way down to when I get to the 100th spot, there's only one thing left to choose. Okay. So the second part of B was kind of funny. I meant to type not if repetition is not allowed, but I accidentally typed if repetition is now allowed. And about half of you read the problem as it was written and got the right answer, and then about the other half, for some reason, read it as I intended it. So I got about 50-50 split. I gave credit for both interpretations. So with replacement, I have 200 to the 100 because I have 200 options for each position in the sequence, and I have 100 positions in the sequence. Okay, so with replacement. Okay. And if you did it without replacement, you should have 200 factorial over 100 factorial, or which is the same as 200p100. Now we have this last one. This is a multinomial coefficient problem. So I have I'm going to make a string of length 100. I'm going to use 20 zeros and 30 ones and 50 twos. So you can just do this in one step if you know about multinomial coefficients, which are explained in one of our video lectures. But if you don't know about multinomial coefficients, you can say, well, I have 100 positions in my string. I can choose 20 of them where I'm going to put my zeros. Okay? And then after that, I have 80 spots remaining. And out of those 80 spots, I'm going to choose 30 of them to put my ones. And then there's no more choice. I just put twos in all 50 remaining spots. So this is the answer. So I choose 20 places out of the initial 100 to put my zeros, and then after that I have 80 places remaining. I choose 30 of those to put my ones, and then I have 50 places and 52s. So there's no more options after that. So some people wrote 50 choose 50, which is true, but 50 choose 50 is just one. So I have 50 places left, and I'm going to choose 50 of them to put the twos. There's only one way to choose 50 things if I only have 50 things. So this ends up being 100 factorial. If you write out the n choose k in terms of factorials, this ends up being kind of a very elegant solution. 100 factorial over 20 factorial times 30 factorial times 50 factorial. Just the 20, 30, 50 that are here are the things that are here. So next we had this prove these identities. So I intended for these to be done by induction, although there is another way to do the first two. We actually, when we proved the geometric series formula previously, we did it without induction. And this one was also done differently. This is a telescoping series, so I had all three of these have another way to be worked besides induction, and people did work each of these problems in those ways. So we have multiple ways to do these, but induction is what I intended. So grading this problem, I realized that a lot of you don't understand induction. So kind of the first problem that we did by induction kind of poisoned you for all of the other ones, because I noticed a lot of people writing down in the inductive step something that was specific to the first thing that we proved by induction. Okay, so kind of the first thing that we proved by induction was some k goes from 1 to n of k, and in that case, for the inductive step, we said, oh, the pn plus 1 term is going to be n plus 1 plus the previous, and then that n plus 1 plus the previous was specific to that problem, but I saw that n plus 1 plus the previous all over the place here. It doesn't have any business here. That was specific to that one problem. So we're going to prove this by induction. So we start with the base case. Base case was n equals 1 or 0. It doesn't matter. So 0 for the first one and then 1 for the other two. But you can use 1 for the first one as well. And I think in the problem I even said for positive integers. So you check it for n equals 0 or 1. Either way, it's fine. I'm not going to write those out. Nobody has trouble with the base cases. So we're going to do the inductive step. So I'm going to assume, so let's start with the first one. I'm going to assume the sum k goes from 0 to n minus 1, 2 to the k equals 2 to the n minus 1. This is the statement Pn minus 1. I'm going to assume Pn minus 1 and prove that Pn is true. I'm going to assume that Pn minus 1 is true and then prove that Pn is true. So if I want to prove that Pn is true, well, I need to start with the left side and then show somehow that it is equal to the right side. Okay? So I could also start with the right side and show that it's equal to the left side. What I'm going to do here is say, well, this is the information I know, and I want to say something about this, so I want to see how these things are related. Well, let me just write it out. I have 2 to the 0 plus 2 to the 1 plus dot 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 plus 2 to the n minus 1 plus 2 to the n. That's what this is, right? And if I just look at the first part, that's the left-hand side of Pn minus 1, right? So this is the left-hand side of Pn minus 1, which means it's equal to the right-hand side of Pn minus 1, so that's 2 to the n minus 1. And then I still have this 2 to the n term over here. So I have 2 to the n plus, or minus 1 plus 2 to the n. That's 2 times 2 to the n minus 1, and that's 2 to the n plus 1 minus 1. So the next one is similar, so I'm going to assume some k goes from from 1 to n minus 1 over 2 to the k is 1 minus 1 over 2 to the n minus 1. I'm going to assume this, and then we use it to prove the next case. So I'm going to have some k goes from 1 to n, 1 over 2 to the k, equals, and again, this is going to be the last term plus the previous terms, and the previous terms are all just what's on the left side over here. So I'm going to have some k goes from 1, n minus 1, 1 over 2 to the k, plus my last term here. So there's a term when k equals n, and then there's all the previous ones, which are just all the terms here. And now by the inductive hypothesis, because I have assumed that this is true, I know this first sum is equal 1 minus 1 over 2 to the n minus 1. And then I have plus 1 over 2 to the n. Right? So this 1 over 2 to the n is over here. This part became here, the first two terms. And now if you work this out, this is 1 minus 1 over 2 to the n. Let's get a common denominator here. Okay. So we're going to do this one. This one's similar. I'm probably going to run out of room and not finish the problem. So I want to assume the statement for n minus 1 and then prove it for n. So again, I'm going to write out the sum for n. K goes from 1 to n, 1 over k plus 1. I'm going to split off the last term and all the previous terms. All the previous terms are going to be n minus 1 over n, and then the last term is going to be 1 over n plus 1. And then you get a common denominator and work it out, and it ends up being n over n plus 1. I'm going to skip the part where you get a common denominator. Okay. More counting. So again, I expected these to basically be free points. These are very standard counting problems. So I'm going to make words of length 8. How many ways can I do that? And I think this problem was directly out of the book. So, again, it's a very problem that we should have been prepared for. How many words of length 8 do I have if I can't use vowels and if I allow repetition? So if I can't use vowels, 26 letters in the English alphabet, 5 of them are vowels and 21 are non-vowels. So if I allow repetition, for each of my 8 letters, I have 21 choices. Okay? So I'm going to make a word with 8 letters, and for each of those letters, for each spot, for each of those 8 spots, I have 21 choices, all my 21 consonants. Okay? So if I have no repetition, then I'm going to have 21 P8. Okay? So I have 21 choices for the first letter because I can't choose any vowel, and then I have 20 choices for the second letter, 19 for the third, etc. And you don't have to write anything else out, but this is 21 factorial over 21, 20, let's see, 21, 20, 19, 18, 17, 16, 15, 14, 13 factorial. Right. So, how many letters start with a vowel? If I allow repetition, well, I have 5 choices for that first vowel. And then if I'm allowing repetition, for each of the other 7 letters, I have 26 choices. So 5 choices for the first letter, just my 5 vowels, and then 26 choices for each of the other 7 places. Okay. So how many words start with a vowel? If I don't allow repetition, I have 5 choices for that initial vowel. Once I've used that vowel, I can't use it again. So for the next choice, for the next letter, I have 25 choices. So I'm going to have 25P7. Okay, so I use one vowel initially. I have 5 choices for which vowel I'm going to use for the first letter. And then after that, I'm going to do 7 more letters with the 25 remaining and without replacement. Okay? So how many words have at least one vowel? So I saw one common incorrect answer here, which was 8 times 5 times 26 to the 7. Right? And so looking at this, you can tell kind of how you came up with this answer. What you did was you said, well, there are 8 positions. So I have 8 choices for the position, and then 5 choices for the vowel, and then 26 to the 7 choices for the other letters. But this is not a good choosing in stages kind of a way to do the problem, because if I do this, I'm going to count certain things more than once. Okay? So let's say here I choose the first position, right? So I choose the first position in the word, and then I choose the vowel A, and then for all my other letters I choose A's. Okay? So this is a choice that I could come up with that 3-stage process. Okay? Now let's say I choose the last position. Okay, so I'm going to choose the 8th position, and then I'm going to choose to put an A there, and then I'm going to make choices for all the other letters. Let's say I make A's for all those. Okay. So choosing a position in which I'm going to put a vowel, and then choosing a vowel to put there, and then choosing all the other letters. If I do this process, this word consisting of 8 A's is going to get counted more than once. In this thought process is going to overcount, because this is going to show up. In fact, this is going to show up 8 times in this process. Okay, so this overcounts. So if you go back to the video lectures, one of the things that I said is an important feature of the choosing in stages thought process is, if I don't want to overcount, it has to be the case that if I'm choosing in stages, if I were to make any different choice at any stage, I couldn't end up at the same response. So if I make some choices and someone else makes some choices, then the end result are 2 different things. But here, I made these choices and got an end result of 8 A's, but then I made a different set of choices. I chose the 8th position instead of the first, but I still ended up with all A's. And so in that situation, I'm over-counting. Okay, so how many words have at least one vowel? Well, here's the good way to do this problem. How many words have at least one vowel? Well, I'm going to have 26 to the 8 possible words. We already computed the number of words that don't have a vowel, so let's just subtract that. Total number of words, total number of words that don't have a vowel. The difference is the total number of words that have at least one. fair coin is, so now some probability. A fair coin is flipped 10 times. What's the probability that we have exactly 5 heads? So I want to count the number of outcomes. So 10 flips, two possible outcomes for each flip. So I have 2 to the 10 total possible outcomes. Now I want to know how many ways can I get exactly 5 heads? Well, there are 10 flips, and I'm going to choose 5 of them to get heads on. There are that many ways to get exactly 5 heads. So there are lots of different ways to get exactly 5 heads. I could have heads, 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 and then tails, 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 tails. That's 1, and then I could have heads, tails, heads, tails, heads, tails, heads, tails, heads, tails. Right, so these are 2 different outcomes, but they both have exactly 5 heads. Right? So I need to count all of the different outcomes where I could get exactly 5 heads. We'll have 10 flips, and I choose which 5 I get the heads on. So I have 100 washing machines, and I have 10 defective washing machines, and I'm going to reach in and grab 20 washing machines at random. What's the probability that 10 of the 20 that I grabbed are defective? So this is a hypergeometric distribution problem, as we talked about. So basically I have 100 washing machines, and I'm going to grab 20. How many different outcomes could there be? Well, there are 100, choose 20. There are this many ways for me to reach into my group of 100 washing machines and grab 20 of them. Okay. So how many ways are there for me to reach in and grab 10 defective and 10 non-defective? Well, there are 10 defective washing machines overall, so there are 10 choose 10 ways for me to, which is just 1. There are 10 choose 10 ways for me to reach in and grab 10 defective ones. And then there are 90 choose 10 ways for me to reach in and grab 10 non-defective ones. And so there are 10 ways to grab the defective one, or 10 choose 10 ways to grab 10 defective ones, and 90 choose 10 ways to grab the non-defective ones. Choosing in stages, I just multiply. This is the total. This times this is the total number of ways for me to reach in and grab 20, 10 from the defective group and 10 from the non-defective group. So there's my answer for B. 20 students are randomly picking these numbers 1 through 100. So I want to know how many different outcomes could there be. So I'm going to line the students up. So I'm going to have student number 1, student number 2, up to a student number 20. And I'm going to record the numbers in a list. So if I do it that way, I have this many possible outcomes. 100 possible outcomes for each student. 20 students, so 100 to 20. How many... What's the question was, what's the probability that they all pick different numbers? So I want to count the number of ways that they could pick different numbers. Well, if I have 20 students picking numbers 1 through 100, well, remember the students are lined up and order matters. So in order to frame this problem, so kind of, I have Alice and Bill, and Alice choosing 1 and Bill choosing 2 is different than Bill choosing 1 and Alice choosing 2. Right? So for order matters here, I'm going to have 100 P20, right? So if none of the students pick the same numbers, so if they all pick different numbers, then that's the same thing as them picking without replacement. Okay, so I have 100 choices, 100 possible choices, 20 choices will be made, and no replacement. So there's this is the total number of ways for the students to pick different numbers, and this is the total number of ways for students to pick numbers, period. So this problem, it was a little bit tricky. So I want to prove that in any group, so say for any 2 people, that pair of people, those 2 people are either friends or they're enemies. Okay? I want to prove that in any group of 6 people, I can find 3 of those people who are all friends with each other or all enemies with each other. But that's not necessarily true if I just have 5 people. If I have 5 people, it's possible that their relationships could be such that for any 3 of them, I have both friends and enemies among those 3. So I'm going to start with the second part. I'm going to start with B. So I'm going to say here's 5 people. Okay. And I'm going to put a line between the friends and not put a line between the enemies. So just grab any 3 of these people. Okay? There's going to be a line between at least 2 of them, and there's not going to be a line between at least two of them, right? So if I grab 3 people that are all in a row, then the 2 outer people are going to be enemies, but they're both going to be friends with the middle person. So if I grab any three people, two of them have to be consecutive, right? So if I grab these two consecutive people and then the opposite person and not a consecutive one, then I'm going to have mutual enemies there, but still a friend there. So it doesn't matter how many. So here's, you have the pentagon here. Line segments represents that those people are friends, and no line segment represents that those people are enemies. So this person and this person are enemies. And here, it doesn't matter which 3 points you pick, there's going to be a line segment between two of those people, and there's going to be two of those people that don't have a line segment between them. So here, I don't have any three people who are all friends with each other. I don't have any three people who are all enemies of each other. So there are a lot of misunderstanding this problem. So the problem says that any two people are either friends or enemies. And then a lot of attempts at the solution to part B had some description in which some people were related to other people by being either friends or enemies, but some people were not friends or enemies of other people, which is not the setup of the problem. The setup of the problem says it has to be the case that for any two people, they are either friends or enemies. And many attempts at a solution to this problem did not satisfy that condition. Okay. So, but now I want to show that if I have at least 6 people, then no matter what, I can find 3 of them that are either all friends or all enemies. Okay. So what I'm going to do is I have 6 people. I'm going to call them A, B, C, D, E, F. Right. So I'm going to have A. I'm going to have B, C, D, E, F, or the other 5. And A is either friends or enemies with B. A is either friends or enemies with C. A is either friends. So for each of these people, they're either a friend of A or an enemy of A. Right. So by the pigeonhole principle, right? Because I'm going to take these 5 people, break them into 2 groups. The group consisting of A's friends and the group consisting of A's enemies. By the pigeonhole principle, one of those 2 groups has to have 3 people. Okay? So just in order to kind of make things easy, I'm going to assume that these 3 people are friends of A. Now, it could be that they're all 5 friends of A. It could be that 4 of them are friends of A and 1 of them is an enemy. But there has to be at least 3 that are all friends or all enemies. So just to make things easier, I'm going to assume that they're friends, but the argument goes exactly the same if they're enemies. Okay? And here I've circled these 3, but it could be the case that these 3 are friends, or 4 of them are friends, or all 5 are friends. I'm just saying at least 3 of them are friends. Okay? And the argument's going to go exactly the same if at least 3 of them are enemies. Okay? So now what I do is, so now these are all friends with A, and now what I want to do is say, well, if any pair of these 3 people are friends with each other, right? So if B and C are friends, then there you go. I have A, B, C. They're all mutually friends. If B and D are friends, then I take A, B, and D. They're all mutually friends. If C and D are friends, then I have A, C, D. They're all mutually friends. Okay. And now, if any 2 of these 3 people are friends with each other, then I'm done. I found 3 mutual friends. But if no 2 of these people are friends with each other, then right here I have 3 mutual enemies. So there we go. No matter what, I was able to find a group of 3 people who are all mutually friends or mutually enemies. So in part A here, so I had some attempts to apply the pigeonhole principle, but it was applied in kind of a strange way, where so you started with people, A, B, C, D, E, F, and then instead of labeling pairs as friends or enemies, you just say A is a friend. And that doesn't make sense, right? So A in isolation isn't a friend, right? You can say A and B are friends, but you can't just say A is a friend. You have to say a friend of whom, right? So relationships exist between pairs of people here. So so my first step in this problem was to split one person off and then look at their relations to the other people. And in that situation, I could apply the pigeonhole principle. But without doing that, I can't apply the pigeonhole principle, because pigeonhole principle was about separating items in a set. And here, I don't have, I'm not going to separate these people into friends and enemies, because that doesn't make sense. Is A, just taken by himself or herself, is not a friend or an enemy. I have to say A and B are friends or enemies. A and C are friends or enemies. I just can't say A is a friend. Right? So the pigeonhole principle would apply if I'm splitting this group of 6 people into 2 subsets, but I'm not, because initially the splitting into two sets are not about individual people here, but about pairs of people here. So what I had to do is split one person off and then say, okay, now I'm going to look at these 5 and their relationship with that 1. And in that situation, now I can break these 5 into 2 subsets by their relationship with A. So the last problem is, what's the probability of a full house given that the first card is the ace of spades? So here, you can use the conditional probability formula. Okay, probability of A given B equals probability of A intersect B over probability of B. But I don't have to do that. So here I have ace of spades, right? So ace of spades. I don't remember what's a spade look like. I don't care. It looks like a diamond, but I don't care. So I just have the ace of spades, and I want to. Okay, so I have that, right? There's no randomness, there's no chance, there's no probability here. That's the first one. That's given. Now I want to just count what's left, right? So how many total hands could I have? Well, I have an ace of spades. There's no randomness to that. So a lot of people had 52 choose 5 in the denominator here, but it's not 52 choose 5 because I already have one card. The randomness is in the other 4 cards. So there's one card, there's 51 left, and I'm going to get 4 of them. So the total number of hands I could have is 51 choose 4. So I'm going to have the ace of spades and whatever other 4 I draw from the 51 remaining. Okay. So the denominator here is 51 choose 4 and not 52 choose 5. Okay, because I already have one card. So now, a more common mistake was to fail to realize that there are 2 ways for me to end up with a full house. I could have 2 aces and 3 of some other rank, or I could have 3 aces and 2 of some other rank. So I'm going to do 2 aces plus 3 of some other rank, and then I'm going to do 3 aces plus 2 of some other rank, and I'm going to count the number of ways to do this, and I'm going to count the number of ways to do this, and then I'm going to add, because there's no overlap, right? Having 2 aces and 3 of another rank is not possible to do if I also have 3 aces and 2 of another rank. So I'm going to count the number of ways to get a full house with 2 aces and 3 of another rank, and count the number of ways to get a full house with 3 aces and 2 of another rank, and add those. And for each of these, I'm going to choose in stages. Okay? So I already have 1 ace. If I'm going to end up with 2 aces, I have to figure out how many ways are there for me to get another ace. Well, there are 3 aces remaining in the deck. So the deck started with 4 aces. I have one of them, so there are 3 left in the deck. So there are 3 choose 1 ways for me to get my second ace. I can get the ace of hearts, or the ace of diamonds, or the ace of clubs. Okay? So now I have to have 3 cards of some other rank. So the 1 rank I have so far is ace. That means there are 12 ranks remaining, so I could do 12 choose 1. Okay? That's how many ways I could get a different rank for my other 3 cards. And then now, whatever rank I chose there are 4 of those remaining in the deck, and I want 3 of them. So there are 4 choose 3 ways for me to get 3 of a different rank once I've chosen what that rank is. Okay? So here I'm picking a different ace from the 3 remaining, here I'm picking a rank from the 12 remaining, and here I'm picking 3 cards from this rank. Okay? And this is the total number of ways for me to get a full house with 2 aces, my ace of spades plus whatever one I picked up here. And it's very easy to see. Well, 3 choose 1 is just 3. 12 choose 1 is just 1, and 4 choose 3 is just 4, so you could write those out. This one is like very obviously 1, so I have 12 ranks to choose from. I'm going to choose 1, so there are just 12 ways to do that. So you don't need to actually have the binary coefficient notation here all the time, but it's just the easiest to put it that way and do it systematically that way for all the problems. So now I want to figure out how many ways can I have a full house with 3 aces. Well, so I already have 1 ace. I need to pick 2 more. So there are 3 aces left in the deck. So I have 1. There are 3 left in the deck. So 3 choose 2 ways for me to pick 2 of the 3 remaining aces. And then I'm going to end up with 3 aces. This one plus the 2 that I chose here. Now there are 12 remaining ranks. There are 12 choose 1 ways to pick another one. And now I have to pick 2 cards from whatever that rank is that I chose here. Okay, so I picked a rank here. Whatever rank that is, there are 4 cards of it remaining in the deck, and I want to choose 2 of them. So I have 4 choose 2. Okay. So there are this many ways for me to pick my other 2 aces, this many ways for me to pick another rank, and this many ways for me to pick a pair from that other rank. So the probability is this fraction. Okay? Total number of hands, total number of full houses with 2 aces, total number of full houses with 3 aces, numerators, total number of full houses, given that I started with that ace of spades.